Hello dear friends, welcome to the lecture of Laplace Transform. In this lecture we shall see a theorem on how to find Laplace transform of a function multiplied by powers of n. That means if f of t is multiplied by t power n, then how to get the Laplace transform. So here is the theorem number 8, which is about multiplication by powers of t. First, we shall suppose the Laplace transform of f of t is equal to small f of s, usual notation. Then the Laplace transform of t power n ft is equal to minus 1 power n into nth derivative of f of s with respect to s, dn fs by dsn, and where n is equal to 1, 2, 3, etc. For positive n is positive integer. So this is the result that we want to prove. When we multiply a function f of t by powers of t, t power 1 may be there, second, or t square, t cube, etc. Then the result becomes minus 1 to the power n into nth derivative of f of s with respect to s. That is the meaning of the theorem. Now we shall prove it. Proof. See, we have Laplace transform of f of t is fs. So we shall prove this theorem by the method of induction. By mathematical induction. And what is the method of mathematical induction? We know we shall have to do two steps. First step is, it has two steps. The first step is prove the result is true for n is equal to 1, and the second is assume the result is true for n is equal to m, and then prove it for next immediate value, that is n is equal to m plus 1. And the first step is, for the case n is equal to 1. So to prove the result or the theorem for n is equal to 1. Now we have this Laplace transform of f of t, capital F of t. The notation is small f of s, and by definition it is integral 0 to infinity e power minus st f of t dt. This is the definition of Laplace transform. And now what we shall do is, we differentiate both sides with respect to s, considering this only. Fs is this, and differentiate both sides with respect to s. Differentiating. With respect to s. See, what we shall get is, left side I shall write d by ds of fs. I shall consider this equation, and this is the actual Laplace transform of f of t, but it is small f of s. Derivative of small f of s with respect to s is equal to, and the right side will be derivative of this integral with respect to s. So thus we have differentiated either side with respect to s. Now we shall see this simplify this right side, or the left side we shall keep as it is, d by ds of fs, first derivative of fs with respect to s, and here is the derivative and this is the integral. So we should differentiate inside the integral, and when we differentiate inside the integral, the derivative becomes partial, because it is with respect to s, and there are two functions. This is a function of both s and t, and this is entirely function of t. Therefore there are two variables now with respect to this derivative is considered, and therefore the derivative inside integral becomes partial. So that is to be noted. This is integral 0 to infinity, and the notation of partial derivative we know is dou by dou s. Partial derivative of with respect to s of e power minus st into f of t dt. And now what is the partial derivative of this? F of t is a constant with respect to partial derivative with respect to s, and therefore only we have to differentiate this term, and that becomes integral 0 to infinity. So the derivative of this exponential function e power minus st is e power minus st into derivative of minus st with respect to s. Derivative of s is 1, so therefore the derivative of minus st with respect to s is minus t, and thus this becomes minus t into e power minus st, and this f of t remains the same, or we may put this in bracket, and this is as it is, remains constant when we differentiate partially with respect to s. So you note this is the derivative of partial derivative of e power minus st with respect to s, minus t into e power minus st, and now we can multiply both sides by negative sign. See here, it is a derivative of fs with respect to s. Multiply both sides with minus sign, minus 1, and that means or we can take this minus 1 on this side. So that becomes negative here, minus 1 d by ds of fs is equal to, now this negative into negative becomes positive, and this right side can be written as integral 0 to infinity e power minus st, and I write this t into ft together, t into f of t dt. You see, we have multiplied both sides by minus 1. This becomes positive, this becomes negative. And what is the right side now? This is by definition, you see, this is a Laplace transform of f of t. This is kernel of the Laplace transform, and therefore the right side is Laplace transform of this function t into f of t, or that is minus 1 d by ds of fs is equal to the Laplace transform of t into f of t. Or we can interchange the sides, that is, or which is L of t into f of t is equal to, t into f of t is equal to minus 1 can be written as minus 1 power 1, and this is first derivative, that is d1 f of s by ds, or there is no need to write 1 here. So d by ds of fs. What this, why I have written here 1, this is first order derivative, and this is minus 1 actually, but I have written minus 1 power 1. So this shows that the result is true for n is equal to 1. See, put n is equal to 1 here, we get L of t into f of t, and right side is minus 1 power 1, which is actually minus 1, and d1 means only d, dfs by ds. So this shows that the result or the theorem is true, or we may say result, the result is true for n is equal to 1. So this is our first step. Now the second step is we shall assume the result is this, the same result. So I am saying this is the result required in the result of the theorem. So we shall now assume the second step, we shall assume the result is true for n is equal to m, and then we have to prove the result is true for n is equal to m plus 1. This is the second step in the induction. Now step 2. Assume the result. Assume or suppose the result is true for n is equal to m, and then to prove the result is true for n is equal to m plus 1. So assume this result is true for n is equal to m, that is replace n by m, and that is what we are assuming is L of t power m f of t is equal to minus 1 power m and mth derivative of fs with respect to s is true. This result is true. Now what we have to prove? The result is, we have to show the result is true for n is equal to m plus 1. And how to prove the result is true for n is equal to m plus 1? Wherever m is there, the result must be true for m plus 1. That is, L of t power m plus 1 into f of t is equal to minus 1 power m plus 1, m plus 1th derivative of fs with respect to s. That is to be shown. Now from this result we have, see, we have assumed this. So I shall suppose this as 1, from 1. From 1, I can write the left side as, this is Laplace transform of t power m ft, or that is, or we can interchange the side, and this side I shall write as left side. From 1, minus 1 power m, mth derivative of fs with respect to s is equal to, and see, the Laplace transform we write by definition, integral 0 to infinity e power minus st t power m f of t into dt. See, this is written as the right side, Laplace transform of t power m into f of t. And now, as earlier, we shall differentiate both sides with respect to s. Differentiating both sides with respect to s. What we shall get? Minus 1 power m is constant, and therefore that remains the same. This is mth derivative of fs with respect to s, and we are differentiating one more time. So therefore this becomes m plus 1th derivative. So d square, the second order derivative, if we differentiate, we get the third order derivative, means order increases by 1. So this will be d m plus 1 of fs with respect to s, m plus 1th derivative. Mth derivative becomes m plus 1th derivative. And on right side, again, as earlier, we are differentiating under integral sign, and therefore the integral sign is the same, and this derivative becomes partial. That is dou by dou s of e power minus st and t power m f of t dt. This is the derivative, or see, the whole expression we have to differentiate partially with respect to s, but this will remain constant because this is a function of t, and only we have to differentiate this e power minus st with respect to s. And as earlier, this derivative is integral 0 to infinity e power minus st into derivative of minus st with respect to s, that is minus t. So that is minus t e power minus st. We have differentiated in earlier step the same, and into t power m into f of t dt remains constant, or further that becomes, now I shall consider this multiplication on both sides by minus 1, multiplying both sides by minus 1, we get. Now what, if you multiply this by minus 1, its power increases by 1. That means the left side term becomes minus 1 to the power m plus 1. No change in this derivative. That is m plus 1th derivative of fs with respect to s. And right side, if you multiply by minus 1, this becomes positive, and thus it is integral 0 to infinity. I write this kernel term first, e power minus st, and then we can multiply these two terms together. T into t power m is t power m plus 1 into f of t into dt. Now you see, what is the right side? By definition, right side is the Laplace transform of this bracket, t power m plus 1 f of t, or that is interchanging the sides, we can write this is the right side Laplace transform of t power m plus 1 into f of t is equal to, and I am writing this side as RHS minus 1 power m plus 1 m plus 1th derivative of fs with respect to s. Now what this shows? This shows that the theorem or the result, this result is true for n is equal to m plus 1. How? We see wherever n is there, we can put m plus 1. So it is t power m plus 1 f of t minus 1 to the power n is m plus 1 and this is m plus 1. So it is exactly the same result. So this shows that the result, this shows that the result is true for n is equal to m plus 1. And this is the second step in the induction. Assuming the result n is equal to, for n is equal to m, we have to prove the result for n is equal to m plus 1. Means the result is true for a certain value, it is true for its next immediate value. And in this way we can combine now two steps. What we have proved in step 1, the result is true for n is equal to 1. Now by step 1, the result is true, or that means the theorem, result means the theorem, result of the theorem, the result is true for n is equal to 1. By step 2, the result is true for n is equal to, see if it is true for n is equal to m, it becomes true for n is equal to m plus 1, and therefore it is true for n is equal to 1. It is now by second step it is true for n is equal to 1 plus 1. See this, and that is it is true for n is equal to 2. And once it is true for n is equal to 2, then it becomes true for n is equal to 2 plus 1. So the result is true for n is equal to 1 plus 1, that is 2, n is equal to 2 plus 1, that is 3, and so on. And so on. The result is true for n is equal to 1, 2, 3, etc. infinite values, positive integer. Therefore the result or theorem is true for n is equal to 1, 2, 3, etc. And this completes the proof. So thus we have proved the theorem using the method of mathematical induction. And the method consists of two steps. First is the result is true for n is equal to 1. Second, assuming the result true for n is equal to m, prove it is true for n is equal to m plus 1. Now we shall have a problem on it. Now we shall solve problems on this theorem or the result. The first problem is evaluate Laplace transform of t square minus 2t plus 1 into sine 3t. Actually this is f of t and it is multiplied by powers of t square, that is t power 1, and here there is no multiplication by t, it is only 1. But at first we shall write this by using linearity property. Solution for problem first. See, we have L of this is t square minus 2t plus 1 into sine 3t, and this can be written as, this is equal to, by using linearity property, it is L of t square into sine 3t. Then minus 2 is constant, can be written outside, L of t into sine 3t. And next is 1 into sine 3t, L of, that is plus 1 1 into sine 3t means L of sine 3t. Now we assume this as first equation. If we have expressed the required Laplace transform in this form, and now on the right side we shall obtain these three Laplace transforms from the last, taking last as the first. That is, we shall find out first Laplace transform of sine 3t, then we shall find out the Laplace transform of t into sine 3t, and then we shall find out the Laplace transform of t square into sine 3t, and then we shall use these values in one, that will give the Laplace transform of the required function. So this is actually the function f of t, because it remains same in each term, or that is multiplied by powers of t. Here it is multiplied by second power of t, here it is multiplied by first power of t, and we have to use this result, multiplication by powers of t. That means Laplace transform of t power n of f of t is equal to minus 1 to the power n and nth derivative of fs with respect to s. So that is to be used. So first we shall find out this one. Now we have L of sine 3t, and that we shall consider, or we may take this as f of t. Now let f of t is equal to sine 3t, or without taking also we shall write it directly, L of sine 3t, and that is by formula it is L of sine at, a divided by s square plus a square, that is 3 divided by s square plus 3 square, which is 9, and this we shall assume as f of s for this fs, because this will be our f of t. And now we will consider this transform L of t into sine 3t using this theorem. Now by theorem 8, Laplace transform of, so this is written for reference only, by theorem 8. So Laplace transform of t into sine 3t is equal to, and this will be multiplication by single power. F of t is now sine 3t, and that is minus 1 to the power n. N is here 1. See the power of t, and therefore it is minus 1 into first derivative of fs into d by ds of fs. Fs is here, this function. So this is equal to minus 1 into, now derivative of d by ds of f of s is 3 divided by s square plus 9. And we can obtain the derivative by the quotient rule, that is equal to minus sign, and if you use the quotient rule, it will be s square plus 9 whole square, the denominator, and at the numerator, denominator into derivative of numerator. See the derivative of numerator is 0, so it is 0 minus 3 into derivative of the denominator, that is s square plus 9 with respect to s, and which is 2s. Derivative of s square is 2s, and derivative of 9 will be 0. So this much is the derivative, or which is minus into minus, that is plus 3 into 2 is 6. 6s divided by s square plus 9 whole square. So this is what we have obtained is L of t into sine 3t. And now we can assume this as 1. So here we have used the result as by 1, and we shall assume this as 2. Now again we want to find t square into sine 3t. Next, Laplace transform of t square into sine 3t. But this can be written as Laplace transform of t into t sine 3t. That I shall write Laplace transform of t into t sine 3t. So because we have obtained the Laplace transform of t sine 3t here, and now this will be fs. This is to be differentiated, or therefore this is by the same result. or otherwise we can use this result repeatedly, that is a second derivative we should have to take, but instead of that we have obtained first step as multiplication by t. Again we use multiplication by t. See, multiplication by t to this function, and that will be now according to the same result, minus 1 into d by ds of this one Laplace, because this is the function f of t now is t into sine 3t, and its transform is 6s divided by s square plus 9 whole square. So d by ds of 6s divided by s square plus 9 whole square. So this is written by 2. You note this. So how we are using the theorem number 8, or otherwise if you we can write this as t square into sine 3t is equal to minus 1 square second order derivative of sine 3t with respect to s. Sine 3t means Laplace transform of sine 3t, that is fs. So second order derivative of 3 divided by s square plus 9. But second order derivative of 3 divided by s square plus 9 means the derivative of the derivative. So here we have obtained the first order derivative, and now again we are differentiating, this means we will get the second order derivative. So instead of writing the result as a second order derivative, we have taken the derivative of the derivative and used the same result for n is equal to 1. So please note this. And now how to get the derivative of this d by ds of that we shall see. Now I shall remove this part so that I can write the further steps here. So that is equal to minus 1 into derivative of this by the quotient rule. So this is equal to minus 1, and you see by quotient rule we should have to write the derivative. The denominator will be square of s square plus 9 square, means fourth power will be there, and this denominator will be at the numerator, that is s square v into du by du by dx, that we have to use quotient rule of derivative. So s square plus 9 whole square denominator into derivative of the numerator 6s, that is 6, minus numerator, that is 6s, into derivative of the denominator. I shall write in bracket. Derivative of this denominator is 2 times s square plus 9 into chain rule we have to use, into derivative of s square plus 9, that is this bracket, which is 2s. So you note this by quotient rule of derivative. And that will be minus 1 is constant. Now we shall simplify this, and while simplifying this we can take s square plus 9 common. So I shall take s square plus 9 common, and in bracket it remains 6 times 6 into s square plus 9 minus, this is taken common, so what remains in bracket is 2 into 2 4 into 6, that is 4 into 6 24, and this is s into s, that is s square will remain in bracket, divided by s square plus 9 to the power 4. So one term cancels with denominator and power at denominator becomes 3. So that I shall write here. So this is the Laplace transform of sine 3t we have obtained. Now I shall write further this step here, that is L of t square into sine 3t is equal to, after cancelling this term it is minus, now you see minus, and in bracket it is 6x square minus 24s square. 6 minus 24 is minus 18, and that minus sign it becomes plus 18s square, and further it is 6 into 9, that is 54. So 18s square plus or from this 6 and 24, 6 can also be taken common. So I shall take 6 common. So if I take 6 here itself common, then it will be 1, and 6 divides 24, and we get here as 4. Note this simplification. 6 into 4 is 24. And now it see s square minus 3s square is this is minus 3s square, and that minus and this minus becomes plus. So it will be 6, and in bracket it is 3s square. S square minus 4s square is minus 3s square, and because of this minus 1 it becomes plus 3s square, and what is remaining is 9. So 9 becomes negative, minus 9 divided by, so divided by the denominator is s square plus 9 cube. One term cancels with numerator. Or finally this 3 can also be taken outside. It is 18. So it is 18 s square minus 3 divided by, so we are taking 3 common, so divided by s square plus 9 cube. So this much is L of t square into sine 3t. Now we shall put these values in equation 1. We have separately obtained L of sine 3t, it is here. We have obtained L of t into sine 3t, it is in second equation, and we have now obtained L of t square sine 3t here. So putting these values in 1, we get the required result. So I shall write here now. Using these values, or we may refer this as 3. The left side is L of t square sine 3t. This is 1, see, this is 1, this must be 2, renaming this is 3, and this is 4. So using 2, 3, 4 in 1. In 1 we get Laplace transform of the required Laplace transform, t square minus 2t plus 1 into sine 3t is equal to, see, it is L of t square sine 3t, that is 18 s square minus 3 divided by s square plus 9 cube. And next is minus 2 times of L of t sine 3t, minus 2 into 6, that is minus 12 s divided by s square plus 9 whole square, and finally it is Laplace transform of sine 3t, that is plus 3 divided by s square plus 9. So this is the answer. In this way we have to use the theorem on multiplication by powers of t. See, this is the required required transform, and we have split in 3 parts, and we have obtained the Laplace transform of each separately. For this we have used the theorem. So thus this completes the solution of the first problem. Now I have written these 2 problems for you to solve. It is Laplace transform of, to find Laplace transform of t into cos at. So find out the write the Laplace transform of cos at. We know it is s divided by s square plus a square. Then multiply it by t, means we have to take the derivative of it with respect to s with negative sign, and this is the answer. And this problem is similar to the problem that we have solved. Instead of sine 3t, here is the term cos 2t. So use the respective formula of Laplace transform of cos and solve this. So please solve these problems yourself. So thank you.